Hello everyone, welcome to our differential equation class. In this video we are going to talk about population models. A population model is a mathematical description of how the size of populations change in time. A population is just a group of individuals. We are going to use what we know about separable differential equations to introduce two very simple population models. One is going to be based on the growth-decay equation. The other is going to be based on the logistic equation. We are going to discuss when we can use, for which populations we can use each of these models. So that's the plan for today. Let's start with a brief review of separable differential equations. A separable differential equation is an equation that can be written in this form. Some function of the variable y multiplied by y prime equal something that doesn't depend on y, so let's call it g of t. Notice this side of the equation has no t explicitly. The t dependence is only through y, and on this side there is no y dependence, so no y dependence. So when that happens, we say the equation is separable. We are interested in these equations because they are super easy to solve. What we need to do is, when we have an equation of that form, h of y multiplied by y prime, and over here we have g of t. The only thing we need to do to solve this equation is to integrate on both sides of the equation with respect, of course, to the same variable, which in this case the dependent variable is t. And that's it. We have solved the equation, because, well, one step to solve the equation still remaining. Here on the left side of the equation we can always do a substitution, and the substitution is that all this is going to be the new variable of integration dy. So if we do that, what we get is that we are integrating the function h of y. Now y is a variable of integration dy, and on the other side is an integral of the function g of t dt, t the variable of integration. So that is actually, once we perform the integrals, this is the solution of the equation in implicit form. No more derivatives. This is the implicit solution formula. So we like to write it down in terms of the antiderivatives. Big H of y, we denote that to be the integral of small h dy, and big G of t is the antiderivative of small g of t. With that notation, the equation, the solution is big H of y, and that is equal some function g of t, and there is a constant of integration that remains there. So this is the exactly the same we wrote before, the implicit solution. And when the function big H is invertible, we can move from here to the explicit solution formula, which is with the inverse of this function, if we can compute it, and then g of t plus c0. And this is the explicit solution. Okay. So this is what we more or less have discussed in the previous class. So Now we are going to use that we know how to solve this type of differential equations, this type here of differential equations, to study population models. And we are going to focus on two main models, one based on the exponential growth decay equation and the other on the logistic equation. So now let's go to the exponential growth decay equation. So then we can talk about the population model associated with that equation. Exponential growth decay equation. What is that? The exponential growth decay equation is simply this equation. Y prime equal a constant times y. A is a non-zero constant. So we have two main cases. When the proportionality constant A is positive, then this equation is called exponential growth. When the proportionality constant is negative, the equation is called exponential decay. And there is a generalization to this equation, and this is when we add here a linear term with a constant, another constant. So that is called the exponential growth decay equation with a linear term. This is the linear term. And well, this is the equation, and now A and B are constants. Of course, A is still non-zero. One comment on the notation before we start solving these equations. We usually write in the literature these equations in terms of the absolute value of the constant here. So let's call the absolute value R. And in the case that B is 0, for example, the linear term is not there, then we write the exponential growth equation like this. Notice that because R is the absolute value of the constant A, then of course R is positive. And this is the exponential growth. And the exponential decay then is going to be negative R, so R is still positive, and this is going to be the exponential decay equation. It's nice to use the absolute value of A in the equation, because then you can see whether if the equation has the negative sign or not. It's easy to see which equation we are talking about, exponential growth, exponential decay, because of the negative sign. Okay, these are very simple equations. You see they are separable equations, very easy to solve. This equation is separable, so it's not separable as is written here, but it can be very easily transformed into a separable equation. The same over here when A and B are constants. To see how we solve these equations, let's instead of working with the most general exponential growth decay with linear term equation with A and B, let's fix A to be 2, B to be 3. And let's find all the solutions to this equation, and later on find the solution of this equation with this initial condition. So, and what we're going to do is we are going to use everything we know about separable equations to solve this equation. Okay, solution. This is an equation that can be written in separable form. So let's write in separable form. So let's start first with the equation we have. Y prime is equal to y plus 3. This equation is written in normal form, but is not in the separable form right now. So normal form. Something like this form. Okay. Now let's write it in separable form. Well, how we can do that? Well, simply by dividing by the whole right hand side. So we divide the equation by the whole right hand side, and we are going to have something of the form y prime. Here is going to be divided by 2y plus 3, and here equal 1. Now the equation is written as separable. And now we know what to do. we now integrate on both sides of the equation. So we have the equation y prime is a function of time. Recall, we are looking for this function divided. I'm going to move everything a little bit to the right so things are nicer. Okay, there we are. Let's keep writing. Then we have 2. Recall, this is a function we are looking for, a function of time, plus 3. And here equal 1. And what we want to do is we want to integrate on both sides of this equation. So we integrate here with respect to the same variable, which is of course the variable t. What do we do now? We do the substitution on the right hand side. So left hand side. On this side we do the usual substitution that is going to change the unknown function into the integration variable. So substitution. That is an I, okay. And what is the substitution? Well, the usual substitution y, the new variable of integration, is the old unknown function. We don't know what that is, but then the differential y is going to be the derivative of this function dt, and this is exactly what we have here. This here is dy. So if we do that, we end up with this give us that we can change y prime of t dt divided by 2 y of t plus 3. The integral of that is now the integral of dy over 2y plus 3. And then it's easy to see that if we can do the integral here, we can do it already. This is just t times a constant c0. So this is where we are. We have to do the integral. Maybe let's write it down a little bit nicer, like this. Differential y over 2y plus 3. This is a y here, by the way. This is horrible. Let's try to do it again. There. And here we have t plus c0. So now what is the integral here on the left side? Well, this is a natural log, isn't it? This is just the natural log of 2y plus 3 absolute value. And I'm forgetting the factor 1/2 here. And also the fact that we have an additive constant, so something like plus c1, that we could always absorb into here, as we are going to do it in a minute. So let's double check that this is the right integration of this integral is that. So let's compute the derivative. So we have 1/2 natural log of 2y plus 3, and we compute the derivative of that. What is going to be equal? I'm just checking. This is just the 1/2 that we have here. The derivative of the natural log is 1 over 2y plus 3, and then we need to multiply by 2 times 2 because it's a derivative with respect to y. So these two cancel that too, and we get exactly 1 over 2y plus 3. So yep, that's this function is the integral of that. Perfect. So now that we have that, well, we still have here t plus c0. And the first thing we are going to do is we are going to absorb the two constants into 1. So from here we get that 1/2 the natural log of the absolute value of 2y plus 3. That is actually t plus c3, let's say, where C3 is obviously C0 minus C1. It doesn't matter, it's an arbitrary constant. So now what we do is we compute the exponential on both sides. Well, we can compute the exponential of both sides, but it's better to get rid of this factor 1/2 first, because we cannot cancel exponential with natural logs if we have this factor 1/2, then we cannot cancel this exponential with this natural log. We cannot cancel because we have this factor here. We need to get rid of this factor, and one way to do it is here, before computing exponentials, multiply everything by 2, the whole equation. So if we do that, we are going to have natural log of 2y plus 3 absolute value, and here we are going to have 2t plus a constant C4. Well, of course, C4 is nothing more than 2C3. It doesn't matter how, I'm just being careful with the names, but people usually is not careful. This is just a constant, this is another constant, which they are related in this way, but just calling it here a constant is enough. So now we can compute exponentials on both sides. Exponential of the natural log of 2y plus 3, and here we are going to have exponential of 2t plus C4. Okay, now we use the rule of the exponentials. On this side, this is just exponential of 2t times exponential of C4 times. It's important here. That on the other side, we have that the exponential and the natural log cancel, and we have here the absolute value of 2y plus 3. Now we get rid of the absolute value, and the way we do that is saying that 2y plus 3 is actually plus or minus exponential C4. This is still a constant, and this is still a 4. And here exponential 2t. Of course, this whole thing now we can call it another constant, C5. And then we have that 2y plus 3 is a constant C5 exponential 2t. Now we move the 3 over here as minus 3, and then everything is divided by 2. Everything. Okay, so let's do that. From here we get that, let's do it slowly. 2y is equal C5 exponential 2t minus 3. We divide everything by 2, and then we have y of t. Our solution is going to be C5 divided by 2 exponential of 2t minus 3/2. Of course, we can call C6, or just simply C, a constant, which is C5 over 2. And here is our general formula for all solutions of the differential equation, which is a constant exponential 2t minus 3/2. These are all the solutions of the differential equation, and they are given in explicit form. So these are explicit explicit solutions. All right, the only thing we need to do now is to work on the initial condition. What was the initial condition? Is up here. The initial condition says that we are looking from all these solutions, the only solution that satisfies that at t equals 0 takes value 5. So we are here, and we say that 5 has to be the solution at 0. But we have the formula for the solution, which is c exponential 0 minus 3/2. Of course, exponential 0 is 1. So from here we get what is the value of the constant, because we have that c minus 3/2 is 5. That implies that c is actually 5 minus plus 3 half. So how we do this calculation? Well, very simply, we have 10 halves plus 3 half, so this is 13 half. We can leave it as 13 halves, or so C is 13 half. Oddly enough, I'm gonna use this formula, which is 13 half, but I want it to keep it like this because you're gonna see in a minute. So the general solution, well, the solution of the initial value problem is, which is only one solution, is, well, let's write the constant first as we did. 13 halves exponential 2t minus 3 half. And this is the formula for the solution of the problem. Okay, so now one comment or one little remark. It's easy to generalize this formula to arbitrary constants a and b. So instead of 2, 2 and 3, we repeat the calculation with a and b. So, and then everything works out exactly the same. The numbers here are going to be different. And I'm going to rewrite this solution as y of t equal, like we had before. This is the initial condition. This is the initial condition plus 3 half. Recall, this is the 13 half exponential 2t, and then minus 3 half. This is the solution of what problem? This is the solution of the equation y prime equal 2y plus 3 with initial condition y at 0 equal 5. This is what we have found. So now it's very easy to generalize this problem, the calculation done in this problem, to a calculation where here we have a. That means here we are going to have a, here we are going to have a, and here we are going to have a. Then if we change the 3 into a b, then here we are going to have a b, here we are going to have a b. And if this 5 is changed into some arbitrary initial condition, then the initial condition is going to be here. And this is going to be the formula for the solution in general for this problem. So it's very easy to prove. Just repeat the calculation with these changes, and we are going to have then the following formula. When you have an arbitrary constant here, here, initial condition, this is the solution of that problem. So this is the differential equation we need to understand and solve. So this is the differential equation to now understand the simplest population model. And the simplest, so let's keep that here. This is an exercise, but you see it's very easy to do. Now that we know, that is not what we wanted. Now that we know that this equation with this initial condition has these solutions, now we can talk about population models. And we are going to talk about population models with infinite food in a minute. So first of all, what is a population model? Well, a population model is a mathematical description of how the size of population changes in time. A population is just a group of individuals, and population growth if they have enough resources, food or space or anything they need. So population is just a group of individuals, and we want to know how the size of the population changes in time according with some hypothesis. And we want a mathematical model for that. And the first model we are going to study is when a population has infinite food, or what is better, infinite resources to grow, infinite resources. So in that case, a population with infinite, a population, let's say a function p of t is the number of individuals in that population at the time t. A population with infinite food resources can be seen experimentally that satisfies the exponential growth equation, this equation, where R is positive is called the growth rate of the population. For example, if we are talking about rabbits, this R, suppose this in years, maybe a population of rabbits has a lot of offsprings in a year, let's say 100. So maybe R is 100 for rabbits. Maybe for humans, if we are talking about humans, maybe it's 2. This growth rate. So that depends on what population we are studying. But for us, it's a constant that is positive. The value of the constant depends on the population, and the interpretation is the growth rate, as we can see here in the equation. And it has units of 1 over time, whatever unit for time you are using. Now, this is a particular case, this equation is a particular case of this equation that we have solved. Is the case b equals 0. So we need to erase b from our solution. And the solution is going to be the initial condition times an exponential with that coefficient, with this coefficient here. So we don't need to solve it because we have solved this equation for all the interesting cases, and we know the solution is an exponential where the exponent has this coefficient here. And this is the initial population. And because of that solution, this is the reason why this equation is called the exponential growth equation, because the solutions are exponentials. And what this equation is saying is that when a population has infinite food resources, then the population grows exponentially. What happens when we add different conditions to the population? For example, suppose we add a constant immigration into the population with a population with an immigration rate k, which with k is the number of individuals per unit time that they are entering into the population. Then one can see that the differential equation in that case is p prime is proportional to p, so the rate of change of the population with respect to time, this is what we are saying here. The population changes in time proportionally to the population that we have at that time, and then we have a constant rate of people entering into the population. So this is the equation, but again, this equation is a particular case of this equation which we have solved. So we know that the solution now is going to be the initial population plus a constant k over r, which, by the way, this has units of population because this has only units of individuals over time. This has unit of 1 over time, that in the denominator the time cancels, and we get individuals only for this constant. Exponential RT, the same as here, and then minus this term. So what happened is the effect of immigration into the population is that the population is going to grow. This term and this term give you the growth without immigration, and then you have this term times this term, which adds to the population. So in the general effect of immigration is, of course, that the population with immigration grows faster than the population without immigration. We can see it here in this equation. At t equals 0, this term cancels that term, and we are at the same initial value that here. Now what we can do is we can have the case of a constant emigration. And emigration is just the immigration constant has the opposite sign. K is still positive. So the solution, the formula for the solution that we had here works for both cases, be positive or negative. So we use the formula and we know what the solution looks like. Now we are going to have a minus here and a plus here. So the effect of emigration obviously is to is to the population grows, but not as fast as before, as this case. And in this case is a little bit different from the previous cases, because now we have non-zero, actually positive equilibrium solutions. What is an equilibrium solution of a differential equation? An equilibrium solution is a constant, let's call it PE, that is solution of the equation. So what is that? So a constant solution of the equation. So let's put a constant into the equation. Let's suppose we put this constant into the equation here. So what we are going to have is the constant PE derivative equal the constant R PE minus K. Okay, but it's a constant, so it doesn't depend on time. So this is 0. So then the constant, the only constant that is solution of the differential equation is the constant K over R. So this is the only constant solution of the equation. This is an equilibrium solution. So this is an equilibrium solution. So we can see that this solution is actually included here in the formula that we have for all solutions. Here we compute the equilibrium solution using the equation, but this solution is actually included here, because if it's a constant solution, that means the initial data has to be that constant, K over R, and when we put that constant in here, look what happens. This whole term disappears and we got the equilibrium solution. So let's put that again. So P of t for that initial condition is going to be P0. So for this initial condition, it's going to be K over R minus this K over R minus K over R exponential RT plus K over R. Of course, this is 0. And we get that for this initial condition, the solution is K over R, which is what we call PE. So for this initial data, the solution formula gives us the equilibrium solution. And how the solutions looks like? Well, in the case that we don't have a immigration or emigration, then it's an exponential that grows, and here we have the initial condition. In the case that we have immigration, then the exponential grows a little bit faster than before, going through the same initial condition, but it grows faster because we have the additional factor here. And when we have emigration, the initial, and we have the same initial condition P0, for example, the solution grows slower, and now we have this equilibrium solution at this particular value where the solution is constant. The solution is constant. And what happens when we have initial data smaller than that? Here, well, the solution is an exponential but decreasing, and it touches 0 at the finite time, so there is extinction in a finite time. This is what happens when there is when the immigration is too high or the initial population is too low. The population collapses to 0. And this is what this exponential growth decay model predicts for the population that have infinitely many food resources with immigration or emigration. Our second and last model for this video is a model of populations that have finite food resources, and these populations are described by an equation that is called the logistic equation. So the logistic equation describes population models or populations with finite food resources, unlike the previous model that has infinite food resources. Okay, what is the logistic equation? Well, the main variable is the function p of t that, as before, is the number of individuals, so the population of the individual we are studying at the time t. And the equation is given by this formula. This is what is called the logistic equation. P prime, the derivative of the population with respect to time, is proportional to the population at that time. So you see we are multiplying by 1. So this term is exactly the same as before in the exponential growth equation. Where is it? Right here. It's the same term, but now we have an extra term. So this term multiplied by that give us the exponential growth equation, but then we have another term here which is going to be quadratic in the population and has a negative sign in front, and that term tries to reduce the growth rate of the population. So the logistic equation is an equation given by p prime equal rp, which is multiplied by 1. This gives us the exponential growth minus p over k. The constant r is the same as before. It's called a growth rate and has units of 1 over time, just as before. And now we have a new constant k, and that constant is also positive, and it's called the carrying capacity and has units of, we can see, units of individuals, because it's gonna cancel the individuals that we have here in this in the numerator. So it has units of individuals. Okay, this is the equation. So let's study the differential equation. Let's see what the coefficients mean. Let's see some particular cases, and then let's solve this equation. This is what we want to do today. So first of all, equilibrium solution. Does this equation has equilibrium solutions? Recall, what is an equilibrium solution? These are constants, PE. Let's call it E for equilibrium. So PE constant that is solution of the equation. Solution of the differential equation. So the differential equation is P E prime. This is an E. It looks like a C, but I swear it's an E. And then this is P equilibrium. And then here 1 minus P equilibrium over K. Okay, but it's a constant in time. Constant in time, which means this here is 0. And now we have a product of two factors, this and that, equals 0. That means either this is 0 or this is 0. So either the constant P is 0 or the constant P is K. So from here we get that P equilibrium multiplied by 1 minus P equilibrium over K has to be 0. And that means what we said. Either P, the equilibrium solution is, that's E are really bad, equal 0, or P equilibrium is equal K. So yes, this equation has equilibrium solutions, and these are the two equilibrium solutions. Okay, so let's write down again the logistic equation, and now let's study what it looks like to be the behavior of this solution of this of the solution of this equation in particular cases. So the first case we want to study, recall P is the population that we are interested only on values of P 0 or bigger. So let's suppose the values of the population. Let's see what this equation looks like when the population is, for example, much smaller than this constant here. This constant is called the carrying capacity, and usually it's a constant that is big, like 10,000, 1 million, 100 million. So it's a big constant usually in applications. What happens when our population is much smaller than this constant k? We want to understand what is the meaning of this constant k. So suppose we have a population much smaller than this constant k. Well, p over k, then, because of that, we divide by k this condition, and we are going to see that this is much smaller than 1. So this number, in this case, is much smaller than 1, and we are subtracting 1 minus that, then this is very similar to 1. So essentially the whole thing here, under this condition, is 1. So the equation looks like the exponential growth equation. So when the population is much smaller than this constant here, the population growth like a normal exponential growth equation. Okay, that's something interesting. Now what happens when the population, because this is gonna grow, isn't it? At some point, because it's growing, it's gonna reach values close to k. It's gonna approach k from below. So what happens when p is still smaller than k but similar values? So suppose this is k and we are getting close to k. What is gonna happen in that case? Well, in that case, then p over k is gonna be smaller but very close to 1. So this here is going to be close to 1 from below. That means that this whole thing is going to be close to 0. But positive, but getting close to 0. So p is increasing. That's what we mean here. P is increasing, but is increasing, but the derivative is starting to get close to 0, which means the solution is going to be close to constant, and the constant has to be this constant k. So the solution approaches the constant k, but never crosses the constant k. What happens when we suppose we have initial condition that is p0 is actually exactly equal k? Well, then we are here and we have an equilibrium solution, which is a solution that is constant in time equal k. So p prime is identically 0, p of t is identically equal k, and this is the equilibrium solution we found before. P equilibrium. Alright, and what happens when the population is bigger than k? Suppose we have an initial condition that the population is 3 times larger than this constant k. Well, then this factor here is gonna be bigger than 1. 1 minus that is gonna say that this is negative. So the derivative is gonna be negative, which means of the population, which means that because of that, that means the solution is going to be decreasing, and we are going to approach k from higher values. So all these cases, what they are saying is we can put all these cases in one picture, and the picture is this. When we have an initial condition that is smaller than k and way smaller, let's say over here, the population grows exponentially, which is what we say here. Then start approaching k, but trying to be constant, always increasing, but trying to be constant, approaching k from below, and this is what happens. When the initial population is k, we have the equilibrium solution, and when we have population bigger than k, well, then the derivative is negative, the solution is decreasing, and then approaches k from the other side. And this is a summary of this behavior. So we can see here what is happening. What is this k then? Well, this k is the population that is approached no matter if you start below k or above k. This is as time grows, all the solutions try to be equal to that constant. So then the interpretation of k now is clear. Is the maximum population that can be sustained by the finite food resources available to the population. So this is the physical meaning of the constant k. The maximum population sustained. The population could be larger at some time, but it's gonna is gonna move in time closer to k, because there is too many people. The population has to reduce to k. If it's too low, it's gonna increase to k. So k, the population tries to go to this value, which is what can be sustained with the food resources available. You increase the food resources, and that means more the constant k increases. Constant k goes here, so everything is the same, but over here. So that is why this equation is a good equation that describes population with finite food resources. The population cannot grow unbounded because the food is finite, and it goes to this constant k. So this parameter tells you how much resources are available to the population. And now what we are going to do in the last part of the class is find the exact solution of this equation, because we know how to do it, because this equation is very easy to write into a separable equation. So let's solve this equation. Here we are choosing R equal 2 and the carrying capacity K equal 3, just to have some values. And let's solve it. Solution. How do we solve this equation? Looks complicated. Yeah, we are not going to do all the steps. We are going to do the main steps only, because we are running out of time. Main steps. And there are going to be several calculations left for you guys to do it. But the first thing to solve this equation is write it in the separable form. That is, the y's on one side, the t's on the other. This is not written in this form, so we need to divide by the whole thing over there. We can leave the 2 here, because the 2, it doesn't matter. So we are going to write the equation as follows: y prime divided by y 1 minus y over 3. And here we are going to keep the 2. Here we could integrate, but I'm going to do, now it's written as separable. So now we can integrate in time, but I'm going to do one little work. So I'm going to multiply and divide the whole thing by 3. So you see 3 here and 3 here. And this 3 I'm going to multiply there and there. So I'm going to cancel the 3 in the denominator, and it's going to appear a 3 here, and I have that 3 over there. So this is going to be the same as something like 3 y prime. I don't like to work with fractions if I can avoid it. Let's move it a little bit higher, nicer. And then here we have a y, and then we have 3 minus y. And this is still equal to. So I can divide by 3. I'm going to divide this by 3, and then we are going to have the equation. I like it in the form is nicer to integrate. Y times 3 minus y, and this equal 2/3. Perfect. So now we can integrate on both sides with respect to time. Let's integrate, and then we are going to have y recall prime of t dt over, down here we are going to have y of t, then 3 minus y of t. This is the integral, and over here we are going to have 2/3, so the integral of 2/3 dt. Now we do the substitution, but again, it's the last time we mention it, but then we are going to start doing it a little bit faster. This is dy, recall. So, well, we don't need to mention it too much. So this is the integral of dy, and down here we are going to have y. Now is the variable of integration, 3 minus y. And over here, on the right hand side, we can do the integral. This is 2/3 t plus some constant c0. Perfect. Now, how do we need to do one integral on the left hand side, and we are done. Okay, how do we do that integral? Well, that is not an easy integral, but there is a way to do it. And if we recall, the magic words that here are partial fractions. So what is that? It's a rewriting of the polynomial on the left hand side. So 1 over 3, so not 3, y, 3 minus y. We are going to rewrite it as an addition of simpler rational functions, one that is a over y plus b over 3 minus y. We want to write it down. So it's possible to write this complicated function as an addition of simpler functions if we choose the right coefficients. So how we are going to choose those coefficients? Well, we do the addition one more time. So y, 3 minus y, that means that the coefficient a is multiplied by 3 minus y, the coefficient b is multiplied by y. So now the term on the left and the right, they have the same denominators. That means we can cancel them out. And we have an equation that is 1 has to be equal a 3 minus y plus b times y, and this has to be true for all y. So, for example, it has to be true for y equals 0, and that means that 1 is equal a times 3 minus 0 plus 0, which obviously means that the coefficient a is 1/3. And then it has to also be true for y equal 3. I'm choosing these two values because when I choose 0, this disappears, and when I choose 3, this other term disappears. So 1 has to be equal a times 0 plus b times 3. And then we have the same result for b. b is also 1/3. And knowing that, we have proven, and we can double check if we want, but we have proven that this rational function 1 over y 3 minus y is actually equal to 1/3 1 over y plus 1/3 1 over 3 minus y. Do the addition and you're gonna see that you get exactly that. And it's not something magical because we chosen a and b, so that happens. So after doing that, now we can do the integral because the integral here is equal to the integral here plus the integral there, isn't it? So now what we have found is now we use this decomposition here. And what we are going to see is that the integral of 1/3 1 over y dy plus the integral of 1/3 1 over 3 minus y dy, this is 2/3 t plus c0. This is what we had before, isn't it? Yes, 2/3 t plus c0. But the integrals now on each integration on the left side are very... we can multiply everything by 3 if we want to, but we are going to do it in a minute. So 1/3, here is the natural log of the absolute value of y. And now we have minus 1/3 the natural log of the absolute value of 3 minus y. Why do we have a minus? This minus here comes because of this minus there. So when you do chain rule, you're going to see that that's the reason of this minus. Plus a constant, but we are going to absorb everything. The new integration constant, we are going to put it, well, let's say plus c1, 2/3 t plus c0. Of course, we are going to put this constant inside here. So now is a good time to multiply everything. So let's move the constant. first, then multiply by 3 the whole equation, all sides, and we end up with the natural log of the absolute value of y minus the natural log of the absolute value of 3 minus y. All that is equal 2t plus 3 c0 minus c1. And of course, we are going to call all this is a constant, so let's call it c2. What do we do here? Well, first of all, right now we can say we have solved the differential equation, and this is the solution in implicit form. So implicit solutions. Solutions in plural because we have one for each constant c2. But we can use the log properties. Properties like, for example, the natural log of a plus the natural log of b. We know this is the natural log of ab. And a similar property is that the natural log of a minus the natural log of b is the natural log of a over b. Properties like that we can use, and we can write then the equation as natural log of the absolute value of y over the absolute value of 3 minus y, and then all that is equal 2 times t plus c2. But all this absolute value is just one big absolute value, so this is the same as the natural log of absolute value of y over 3 minus y. And this is another way to write down the same solution in implicit form. It's a little bit nicer, plus c2. And we can do it even better. And we can say, for example, that if we compute exponentials on both sides, y over 3 minus y, this is equal exponential 2t plus c2, and recall this exponential is just the exponential of 2t times the exponential of c2, and here the natural log and the exponentials cancel out, and we have absolute value of y over 3 minus y is equal exponential c2 exponential 2t. We can get rid of the absolute values, and then we end up that y function of t over 3 minus y function of t is actually equal okay, let's do it here to save a little bit of space. Y over 3 minus y is plus minus, this is because we got rid of the absolute value, exponential c2, and here is exponential of 2t, and of course this constant here is going to be now c3, which is what I wanted to write here, c3 exponential 2t. So this is another way to write the same solutions that we wrote before, another implicit form, implicit solutions. Again, plural because we have many, because of that constant. Well, now if you do, now is when we start skipping some steps. If you do some work, so some work here, algebraic work only, you can rewrite this equation in explicit form as follows. 3. Then this is the same constant c3 we had before, exponential 2t, and then divided by what? By 1 plus c3 exponential 2t. So, and now we have our first expression or explicit solution. Explicit now. Solutions, and there are many, so solutions. Okay. some algebraic work. So you need to figure it out, how to get from here to here, but of course you multiply by that factor there, then distribute, then reorganize, and well, you end up here. And now you can do a little bit more of work, not much work, but a little bit of work, and you can end up in a nicer form for the explicit solution that is something of the form 3 here divided by, not exponential, divided by 1 plus some constant C4 that you need to figure it out what that is, exponential, and now exponential minus 2t. But with some work you can get from here to here, not a big problem. And again, this is an explicit solution. There are many ways to write the explicit solutions. Many, because we have one for each value of the constant, in this case C4, which is related to the C3. Okay, and now the constant C4 is fixed by the initial condition. Recall the initial condition is y at 0 is equal 7, if I remember correctly. No, it's not. I didn't write the initial condition. Okay, so let's write it. So because I want to solve an initial value problem, so initial condition y, I forgot to write the initial condition, equals 7. So let's make it like that. This is the problem we want to solve, actually. Okay, we found all the solution of this equation, and now we want initial condition. That initial condition here is gonna fix, of course, the constant C4. And we are going to need to do some work, but the work is essentially 7 is equal to the function at 0, which is 3 over 1 plus C4, because exponential of 0 is 1. And now from here you get C4. It's gonna be some work. There has to be some work to be done, but you're gonna end up that after some work, C4 is actually minus 4/7. Cool. And then a little bit more work, but it's all algebraic work. You're gonna end up with more work that the solution can be written in this very nice final form, which is 3 multiplied by 7. I like to write it like that. You will see in a minute. 7 here plus 3 minus 7 exponential negative 2t. And recall, this is the solution of the equation y prime equal 2y 1 minus y over 3 with initial condition y at 0 equals 7. So the solution of this equation is that equation there, that function there. I like to write the solution in this way because all the constants are visible. So for example, the constant here, the growth rate that we usually call R, appears here. The constant 3, which is the carrying capacity, appears here and here. And the constant 7, which is the initial condition, appears, well, here, here, and here. So then it's not going to be a surprise to realize that when we do repeat the same steps we did before, the problem that we wanted to solve ends here. It's not going to be a surprise, and it's an exercise for you to do, that in the general case, when we have r instead of 2, then we need to put here r in the solution. When we have k here instead of 3, we need to put here k and k. And when we have y0 instead of 7, we need to put y0, y0, and y0, and then you end up with this expression for the solution. K y0, y0, k minus y0, exponential negative rt. And this is the solution of the initial value problem for the logistic equation with some initial condition. We are going to further study these solutions in a following video, but if you have a computer, you can actually graph these solutions for arbitrary constant, for arbitrary constant k, y0s, and r, and you are going to end up with something that looks like this, and which agrees with the previous analysis we did on the equation. We are going to have equilibrium solutions k and 0, and then if the initial data is between k and 0, the solution is increasing, approaching k. So this is done with the computer for different values of y0. So let me put here, this here is one y0, this here is another y0, this here is another y0, and so on. This is a y0. These are different initial conditions. So for different values of initial condition, you get, for each value, you get one solution. If the initial condition is in this interval, you get solution that increase. If the initial condition is k, you have the constant solution. If they are above k, they go back to k, the solutions. So because of this behavior that the solutions here for many different initial conditions bunch up as time grows, bunch up along this solution, we call this solution a stable equilibrium, and the solutions here go away from 0. They, as t grows, they go away. We call it unstable. So this is the general behavior of the solutions of the logistic equation. In the next video, we are going to go a little bit deeper into these solutions and these models for population with finite food resources. But here is a good place to stop.